Assalamualaikum. Welcome back to Sir K Lab's Physics and Chemistry tutorial for high school students. In today's episode, we analyze and solve a problem that involves the rate of thermal conduction. So stick around, watch and learn. In heat conduction, thermal energy is transferred from a hot body to a cold body by way of atoms and molecules colliding with one another. Consider an elongated rod as shown in this figure. Its hotter end, labeled capital A, and its cooler end, labeled capital B. Since the two ends of the rod are said to be in thermal contact, the thermal energy flows by way of this mode known as conduction. We assume that the rod is a good heat conductor. And how fast does the transfer of energy take place is called the rate of thermal energy conduction, denoted here by big Q, or heat, divided by time small t. And the formula for the rate of thermal energy conduction is big Q over T equals K times capital A times delta capital T all over capital L, where capital A is the cross-sectional area of the rod. Capital L refers to the length of the rod. Delta capital T is the temperature difference, T sub B minus T sub A. And small letter k is known as the thermal conductivity constant. And its definition or formula is also based from the equation for thermal energy or rate of thermal energy conduction. All right? So, take note that based on this equation for rate of thermal energy conduction, we see that uh, the rate of energy transfer, okay, is directly proportional to the cross-sectional area of the transmitting medium. All right, that's capital A. It's also directly proportional to the change in the temperature delta T, but is in fact inversely proportional to the length of the transmitting rod. All right? Some common materials with their conductivities are given in this table. Take note that the SI unit of thermal energy conductivity is watts per meter Kelvin, which is just the same as joule per second meter Celsius degree. Notice also that most of these materials with high values of K are the common metals, right? Like silver, copper, gold, aluminum, and tungsten, all right? Which we know are also good conductors of electricity. Now, look at uh, the value for the thermal energy conductivity of air, all right? Why do you think people in hot places, okay, like the Middle East, people there prefer to wear loose clothes during hot summer months? And if you look at the key values of wood as well as hollow blocks, all right, you'll see that the key values of wood are relatively much lower compared to hollow blocks, right? So, can you guess why people in rural areas prefer wood over hollow blocks as materials for their shelters or houses? So let's now look at our question number one. Two bars are placed between plates whose temperature are labeled here as T's of hot and T's of cold. The thermal conductivity of bar 1 is 6 times that of bar 2, or K sub 1 equals 6 K sub 2. But bar 1 has only one-third the cross-sectional area. That is, A sub 1 is equal to one-third of A sub 2. Ignore any heat loss through the sides of the bars. Question is, which one of the following correctly describes the heat conducted by the bars in a given amount of time? Alright, so once again, the question is, uh, which of these options, A, B, C, and D, okay, correctly describes the heat that is being conducted by the two bars in the same amount of time? Alright, so once again, uh, looking at this diagram, alright, we're talking about uh, two bars, bar 1 and bar 2, all right, having the same length, all right, the same length, but they differ in terms of their thickness or cross-sectional area. It was mentioned that bar 1 has a cross-sectional area that's only one-third that of bar 2, all right, and that the thermal conductivity constant of bar 1 is 6 times, okay, larger compared to that of bar 2. All right? So that means the two bars are not made of the same material. All right? So aside from the length and aside from the temperature of the hot ends and the colder ends of the two bars, right, which are assumed to be the same or constant, all right? So we have the three variables, the length, the delta t, and the time small t are held constant. All right? It's only the cross-sectional area and the thermal conductivity value of the two bars that differ. And our task is which among these four options correctly describe the amount of thermal energy that is being conducted, all right, from the hot end of the bar to the colder end, all right, for the same amount of time. So, our concept, of course, is based on the fact that uh, the amount of heat, big Q, all right, is just equal to the product of the constant small k, the cross-sectional area capital A, the change in temperature delta capital T, all right, multiplied by the time elapsed, all right, but divided by the length of the bars, all right. Earlier, we introduced the meaning of rate of thermal energy conduction that was denoted by big Q divided by small t, all right. But since we are only describing the amount of thermal energy, big Q, so what happened was that we just transpose the time, small t, to the right side of the equation, all right? So this is what happens. So that means in comparing the amount of big Q, all right, of bar 1 to that of bar 2, we come up with this comparison, all right, where in Q1, all right, the amount of thermal energy that's being transferred by bar 1, okay, it's only 6 times 1/3, all right, multiplied by the value of Q2, all right. 6 is based on the fact that the thermal conductivity constant of bar 1 is 6 times that of bar 2, while the fraction here, 1 over 3, refers to the comparison of the cross-sectional area, all right, which was mentioned earlier that the cross-sectional area of bar 1 is only 1/3 compared to that of bar 2, all right. So combining the two relationships, all right, and uh, in as much as the other three variables, all right, the uh, the length, the small t representing the time, and the change in temperature delta big T are all held constant. So this is just what we came up in comparing Q1 to Q2. So this means that Q1 is twice the value of Q2. All right, because 6 multiplied by 1 over 3 is 2. All right, so the amount of energy that is transferred by bar 1 is just twice, okay, the value of heat that is transferred by bar 2. In short, our answer to question number 1 is option letter B, where Q1 is equal to twice the value of Q2. For our last question, number 2, one end of an insulated metal rod is maintained at 100 degrees Celsius and the other end is maintained at 0 degrees Celsius by an ice-water mixture. The rod is 60.0 centimeters long and has a cross-sectional area of 1.25 centimeters squared. The thermal energy conducted by the rod melts 8.50 grams of ice in 10.0 minutes. Question is, find the thermal conductivity constant, small letter k, of the metal. For our solution, let's first identify the important data mentioned in the question. All right? So, one end of the rod has a temperature that is maintained at 100 degrees Celsius. So that is our uh, temperature T sub 1. All right? The other end of the rod, okay, is kept at the temperature of the ice. All right? So certain amount of ice is placed on the other end of the rod, whose temperature is labeled here as T sub 2, and it is equal to 0 degrees Celsius. The length of the rod is given and is equal to 60.0 centimeters. All right? And the cross-sectional area of the rod, okay, is also given 1.25 centimeter squared. And the amount of ice, all right, that melts because of uh, the heat that is being conducted by the rod, all right, in a certain time elapse, all right. This is the amount of ice that melts without changing its temperature, all right, equal to 8.50 grams. All right. We are also given the constant known as the latent heat of fusion of ice, equal to 33.5 raised to the fourth power joules per kilogram. And the time during which the conduction takes place, small letter t, is 10.0 minutes. So that's equivalent to 600 point second. This means that we are emphasizing the three significant figures of the original time, 10.0 minutes. All right? And our target variable is to determine the constant thermal conductivity K of the rod. All right? Which eventually will tell us, okay, what material is the rod made of. All right. So our formulas or equations, first, we need to know the amount of heat, okay, that is conducted from the hotter end of the rod to the cooler end of the rod in a time of 600 seconds. So that is equivalent to the amount of heat or thermal energy responsible for melting this amount of ice. All right. So the mass small letter m is given. That's the mass of ice that melts, and also the latent heat of fusion of the ice, which is also given. All right. But we need to know the amount of thermal energy, okay, that melts the ice, which is simply the same as the amount of thermal energy that is conducted, all right, by the rod in a time of 600 seconds. All right. So the other formula, of course, is based on the formula for determining the amount of heat Q. All right. So we already introduced this earlier. What we want uh, in answering the question, finding the value of the thermal energy constant K, is to isolate this formula and come up with that formula, working formula for the constant K, which is simply equal to the product of Q and the length L all over K, the cross-sectional area A times the delta capital T, or change in temperature, and the time small letter t. All right? So executing this formula, Q equals M times LF, that is the amount of thermal energy that melts this amount of ice, 8.50 times 10 to the negative 3 kilogram, all right, multiplied by its latent heat of fusion, 33.5 times 10 to the fourth power joules per kilogram, we have the amount of big Q equal to 2,850 joules. So that brings us now to computing the value of the constant K using this formula. All right? And substituting, we have the amount of computed big Q, which is 2,850 joules, multiplied by the length of the rod, 0.600 meters, all over the cross-sectional area, expressed here in terms of meters squared, 1.25 times 10 to the negative 4 meters squared, times the change in temperature, 100 Celsius degree, and multiplied also by the elapsed time of 600 point seconds. So doing our math, we arrive at the value of the constant K, all right? First, the result of multiplying the quantities in the numerator, that gives us 1,710 joules meter, and the result of multiplying the quantities in the denominator, giving us this value, 7.5 meters squared Celsius degree second. So further simplification, we finally arrive at the value of the thermal conductivity constant K equal to 228 watts per meter Kelvin, which incidentally is also the same as 228 joules per second meter Celsius degree. All right, so comparing the experimental value of the thermal conductivity of the rod, small k equals 228 watts per meter Kelvin, it looks like that among the materials given in this table, that value, okay, is very much close to that of the metal aluminum, whose theoretical conductivity constant is 247 watts per meter Kelvin. So that's not very far from the experimental value that we obtained in our problem. So that ends our discussion of this topic. Okay, till the next episode, mabuhay, Masya Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.